In this video, I want to work through some examples with limits. So we're going to evaluate 3 different limits today and look at some different situations that can result, starting with those that we're most comfortable with, that are easier to work with, and then working on to the ones that have the most application in calculus going forward. So let's begin with an example where we want to find the limit as x approaches 1 of 6x to the 5th minus 3x squared plus 7x. And I'm going to assume that you are able to find some information about basic limits and some information about properties of limits that can verify the steps that are going to be taken here. But basically, we're going to be operating with the assumption that limits can be moved through any continuous function. So here it goes. The first thing we're going to do is distribute the limit to all 3 terms. So now we're going to have the limit as x approaches 1 of 6x to the 5th minus the limit as x approaches 1 of 3x squared plus the limit as x approaches 1 of 7x. And each of these terms inside the limit has a constant coefficient. We know that we're able to move those constant coefficients through limits, and as a result, we can write 6 times the limit as x approaches 1 of x to the 5th minus 3 times the limit as x approaches 1 of x squared plus 7 times the limit as x approaches 1 of x. Finally, and this is going to be a move that's not often introduced, maybe as a theorem at the beginning of chapters about limits, but because we can move a limit through a product, we know that we should also be able to move a limit through a power. So we can put it inside the exponents in these terms, in the first 2 terms we have here. So we're going to continue, and now we're going to have 6 times the limit as x approaches 1 of x, all raised to the 5th power, minus 3 times the limit as x approaches 1 of x raised to the 2nd power. And just for some continuity between all these things, we'll go with plus 7 and then the limit as x approaches 1 of x raised to the 1st power. We don't need to have that written down. All right. So a property or a basic limit, I guess, that we should be familiar with is the limit as x approaches a of x is equal to a. This is a theorem usually given near the beginning of any chapter on limits. Without formal proof at this point, we're still dealing with informal understanding of limits in general. So applying that to this specific problem, we get the limit as x approaches 1 of x is equal to 1. In other words, at this step right here, what we're really doing is plugging in 1 for x. And a good question would be, if we're going to plug in 1 for x now, why would we not just plug in 1 for x at the beginning of this problem? And the answer is that we, in fact, should simply plug 1 in for x at the beginning of this problem. So we can write the limit as x approaches 1 of 6x to the fifth minus 3x squared plus 7x is, in fact, equal to 6 times 1 to the fifth minus 3 times 1 squared plus 7 times 1, or 6 minus 3 plus 7, which is equal to 10. So the limit, as x approaches 1, of 6x to the fifth minus 3x squared plus 7x equals 10. Because we're able to plug 1 into this specific function that we're evaluating the limit on, and get something equivalent to the value of the limit. And there will be a lot of functions and a lot of values where we'll be able to take limits in that way. It's sometimes referred to the plug and chug method. It turns out, though, that more interesting things happen when the plug and chug method breaks down. So we'll look at a couple of examples of that. Starting with this example where we have the limit as x approaches 3 of 1 over x minus 3. And we can go ahead and try plugging in. It's actually not a bad idea on most limits to attempt to plug in the value that we're trying to approach with x. So if we do that, we get 1 over 3 minus 3 is equal to 1 over 0. Now, 1 over 0 is undefined, and it will always be undefined. As a result, we can say that this limit does not exist. And let's make a quick sketch that helps to illustrate that. Oops. There we go. We know that for, let's write this as a function, f of x equals 1 over x minus 3, that a rough sketch of the graph has a vertical asymptote at 3. And therein lies the problem for this graph. On the one hand, when we have x values that are greater than 3, we have positive outputs that go something like this. When we have x values that are less than 3, we have negative outputs that go something like that. So when we're approaching 3 from the left, our function is headed towards negative infinity. When we're approaching 3 from the right, it's headed towards positive infinity. So in general, where functions have vertical asymptotes, their limit cannot and does not exist. Now let's look at an alternative example. Here we've got the limit as x approaches 3 again. And this time we're going to have x minus 3 in the numerator, x squared minus 9 in the denominator. Attempting to plug in the value we're making x approach gives us 0 over 0. Now 0 over 0 is undefined, but in terms of limits, we have another special name for it. We say that this is an indeterminate form. And what that means for us is maybe the limit exists. And it will be our job to work through some algebraic manipulations of this function that we're trying to find the limit for, in order to determine whether there really is a limit or whether there in fact is no limit. So we're going to continue on. Our original limit, it should be clear. Limit as x approaches 3 of x minus 3 over x squared minus 9 is exactly the same as the limit as x approaches 3 of x minus 3 over x plus 3 times x minus 3. Right? We use difference of squares to factor the denominator, and these are equivalent statements. Now the thing that's not immediately clear is that we can continue through this process to say that the limit as x approaches 3 of what we have here is actually equal to the limit as x approaches 3 of 1 over x plus 3. In other words, the x minus 3 in the numerator and denominator can cancel, and we still have an equivalent limit. Now that's not to say that the functions x minus 3 over x squared minus 9 and 1 over x plus 3 are exactly equivalent. In fact, they have equal outputs at every value of x except for x equals 3. So we'll come back to that thought in a minute. But their limits are equivalent, and we can move on. Then now there's nothing to stop us from plugging in the value we're making x approach. When we put it in at this point, we get 1 over 3 plus 3 is equal to 1/6. So this limit, although when we try to plug in 3 originally, we get an indeterminate form 0 over 0. If we work through a process of simplifying, canceling, we find a limit we can evaluate, and it turns out that they are equal to 1/6. So let's think a little bit about what this means graphically. I'm going to come down a little bit and try to get a graph drawn here that we can use effectively. So I don't think we need much space up and down. A little bit of room left to right. Okay. So, if we're talking about this function, f of x is equal to x minus 3 over x plus 3 times x minus 3, then we know by the way that we've graphed rational functions in the past, the denominator will be 0 when x is equal to negative 3, and the numerator will not be 0 at the same time. So we have a vertical asymptote at x equals negative 3. And I've worked a little bit on this already, so I'm going to fill in some other points that we know without giving us too much time to think about it. So if we make x equal to negative 2, then we get 1. If we make x equal to 0, we get 1/3. And horizontal asymptote on this graph, we should know, since the degree is greater in the denominator than it is in the numerator, we have a horizontal asymptote at on the x-axis where y is equal to 0. So we're coming down from this vertical asymptote through these points, and we're continuing on out in this direction, getting closer and closer to the x-axis. When we get to 3, though, with our x value of 3, then all of a sudden we're undefined. But then we continue on through this same path, right, out towards positive infinity for the x value, but approaching 0. And over here on the other side, making some assumptions about where these points are supposed to go, but I think they're probably right, and it's not really important. Over here on this side, we've got something that looks like that. So for this function, we have a hole in the graph, and before we didn't really know where to put it, but it turns out that our output should be right here at 1/6.